Thank you again. So, yesterday I finished the lecture with giving two applications, one related to the Weinstein conjecture for contact type hypersurfaces in R2n, or more generally in subcritical Stein manifolds, or even more generally for manifolds for which symplectic homology vanishes. Second kind of application was obstructions to exact Lagrangian embeddings, yeah, inside manifolds for which symplectic homology vanishes. So I owe you a few of the proofs, right? So I'll spend probably half of the lecture today by giving some proofs of what I put on the blackboard yesterday, and then the second half there's going to be new material. Yeah. So first of all, someone asked me about more references, so additional reference, which I'm adding only because it's published here at Ensayos Matemáticos, so it's myself in Ensayos. Yeah, so that's in 2004, I believe. That's a survey paper on symplectic homology. So, I mean, since there's been this paper by Seidel, Biased View, which is absolutely fantastic, yeah, full of great ideas, I kind of quit referring to this one, which I think is left behind. Yeah, but you may find it still useful. So, then about the homework. Yeah, so I was owing you a computation for the linearized flow yesterday. Flow of h of z equals az squared on Cn, right? So here my convention, and maybe it's good to emphasize, again, my convention is such that the Hamiltonian vector field is defined by this relation, yeah? And as you have seen in Alberto's lectures, this is opposite to what you get from the Hamilton equation, right? And here you get that xh at the point z is just minus 2a jz. So it's linear, but it's not what you would think. It's minus. There's a minus in front, right? It goes the other way around. And the flow, of course, is linear as well. So phi th of z, that's minus 2a jt z. And the linearized flow, right, is the same thing. So d phi t h at the point z is going to be a map symplectic from R2n to R2n, whoops, yeah, which is just multiplication by e to the mi to ajt, right? And you ask yourself, what's the Conley-Zender of this thing, right? And it turns out, you can even take it as a normalization axiom for the Conley-Zender index in this case, that the Conley-Zender index of this path, right, ajt, as t varies from 0 to 1, so you have this path of symplectic matrices, right? Actually, it's not good to draw it this way. It starts at identity, and it's going to do this a certain number of times, right? Okay? Until it hits here. And it passes through identity exactly for t equals k pi over a, right? And as a matter of fact, the Conley-Zender index is computed by looking how many times you go through the wall of matrices which admit eigenvalues equal to 1, right? In this case, along this path, it's just the identity which does so, right? So you have to look at all instances where you hit the identity, right? So here k takes values from 0 to the integer part of a over pi, right? And the first time you hit the identity, because it's the time you start, right? You just have to count half of the eigenvalues. Yeah. So here you get a contribution which is going Because of the minus sign, there's going to be a minus in front, and you have n, and then 2n times a over pi. Yeah. So it's fine. It grows linearly with a, as I have said yesterday. Now you have an explicit expression, and note that it is negative. Yeah. And the reason why I wanted to emphasize this is that actually my convention is that the degree is given by minus the Conley-Zender index, and this is a manifestation of that. But there's other reasons coming from the index formula. Yeah. So my convention is that the degree star is minus the Conley-Zender index. So yeah. So if you know the Conley-Zender index, this is a standard computation, and if you don't know it, it's a good exercise to know enough about it in order to understand it. So in both cases, I think it's useful. Yeah. All right. Now, what I was, I have put yesterday, so concerning the definition of symplectic homology. I don't remember whether I have denoted yesterday the Liouville domain by W or V. Let's say W. Yeah. So I had put this, I have said that we define as a limit over A of Floer homology of these Hamiltonians HA. And this HA belonged to that class of admissible Hamiltonians with maximal slope equal to A, right? So the first question was, why is it well defined, and for what type of complex structure? So what kind of, I remind to you the questions, what kind of almost complex structures, right? And for the well-definedness, what I mean is that we're on a compact manifold, right? And as you have seen in Mihai's lecture today, it's important in order to achieve compactness, Gromov compactness, to know that a priori your Floer trajectories are contained in a compact set, right? So you need a priori bound, a priori C0 bound on Floer trajectories. Floer trajectories, yeah? And then the second thing was that for A smaller than A prime, you also need a continuation map. HA smaller than HA prime, continuation map. So this is a name, continuation map. You're not supposed to know what it is. I'm going to explain it right now. And this direct limit is taken with respect to this directed system, right? And there was also another question which I do not write, which was, is this object dependent only on the asymptotic slope, right? And that I somehow hinted at yesterday, because when I computed the homology of the ball, I was telling you, well, we're able to deform a Hamiltonian in an arbitrary way inside a compact set, right? Because I was replacing this tiny Hamiltonian, C2 small, by something which had a very specific form in the case of the ball, right? So if you agree that you are able to deform the Hamiltonian arbitrarily on a compact set, then you are done, right? This thing is independent of the Hamiltonian as long as you keep the slope fixed, right? Good. So concerning the almost complex structure, recall the geometric setup that we have on the symplectization 1 infinity cross the boundary of W, right? We have as a symplectic form D of R alpha. Yeah? And the boundary of W that at a point, if you wish, Rx, right? The tangent space of this thing splits, of course, as R, which is the tangent space to that, direct sum, the vector space, the line spanned by the Reb vector field, R alpha, and then direct sum psi, which is the kernel of alpha. Of course, alpha is a one form, and the tangent space splits according to the kernel, and then something which is not in the kernel. Yeah? And so, definition, yeah? J on almost complex structure on 1 infinity cross boundary is cylindrical, or sometimes people call it SFT type, and this SFT has to do with are the initials from symplectic field theory. Yeah, which is one of those mantras that scare and inspire awe at the same time. And anyway, this is, I'll call it cylindrical from now on, if it satisfies the following. J is going to send R d by dr on the Reb vector field. And conversely, of course, the Reb vector field is sent to minus this. And J restricted to psi, or rather I will say J preserves psi, right? And is independent of R on psi. And R is the coordinate here. That's another more, if you wish, conceptual way of phrasing it is this thing is that J on the first level equivalently, yeah, at R equals 1, J d by dr is R alpha. Also, J preserves psi, and J is invariant under homotheties. And by homothethy, I mean, I don't know how I pronounce, homothethy, homothethy. I would say homothethy, I'm not sure. So by that I mean a map which sends Rx to some CRX. Yeah? And that's exactly what forces that. Okay? So this is more conceptual and gives you how to say, a feeling of the fact that this R is not there in order to destroy the symmetry. On the contrary, all this cylindrical end, right, this is the half of symplectization, is the same everywhere from the almost complex point of view. Okay? All right. So that's a definition. These are the almost complex structures that are going to do the job. And so from now on, we consider on the completion W hat almost complex structures JT with T in S1, right, which for R large enough are cylindrical. And independent of time. Okay? These are the almost complex structures for which we're going to be able to prove an a priori bound on trajectories. Yeah? And now I want to write a lemma. Yeah? Lemma. So let J as above, right? Then let H A, right? Let H A in H A, right? And okay. Then for there exists a compact set K such that for every 2 periodic orbits, gamma minus, gamma plus, 1 periodic orbits of XHA, and for every U Floer trajectory, meaning it satisfies, maybe I should write also HA and J here, i.e. DSU plus J DTU. Maybe in order not to create ambiguity, I'll still stick to putting the T here, right? So that you know that it depends on time. JT of U DTU minus XHA of U equals 0. Yeah? Then the image of U is contained in K, right? And this is what we need in order to conclude that the homology group is well defined, although we are on a non-compact situation, which means that the relation d square equals 0 holds, right? This relation d square equals 0 holds because we are, as Mihai explained in his lectures, we look at one-dimensional moduli spaces, and we know that they can degenerate, right, only to broken trajectories, right? And this is ensured by the fact we are inside a compact set. Otherwise, there may be something that happens at infinity, right? The trajectories, this space could be non-compact even up to breaking because the trajectories could escape to infinity. Yeah. So at this point, I want to emphasize the following message for the people who will earn their daily bread from Floer homology one day. So whenever there's a loss of compactness phenomenon, there's something interesting going on, right? So this type of loss of compactness has not been investigated, right? So we say there's a loss of compactness if, yeah? What kind of, yeah? How do these trajectories escape to infinity? Just in any way? Of course not. The holomorphic curve never does something just like that. It's just something that we don't understand yet. Yeah? So that's a message. All right. So how are we going to prove that? Of course, the periodic orbits of HA are all contained in a compact set, right? Because HA is linear at infinity, and the slope is not the period of a closed characteristic, and therefore outside a compact set there's no one periodic orbit. Okay? So all one periodic orbits of HA are contained in compact set. Right? So I'm going to choose pick K, compact say, let me call it C. Pick K such that K contains C. Oh, sorry. I'm just going to say pick K to be equal to some, to W, whoops, the union 1 some capital R cross boundary, right? With R large enough, yeah, such that this K contains all the periodic orbits. The Hamiltonian HA is linear, is AR plus B for R bigger than R, right? And J is cylindrical and independent of time, and cylindrical for R bigger than R, right? So I claim that all Floer trajectories are contained in this guy. And this comes from the following fact. Yeah, this comes from the following fact. Let's decompose. So let us look. So the claim is that K satisfies the requirements. Yeah. And so by contradiction, if not, right, let U such that the image of U is not contained in K, right, and pick such that the image of U is not contained in K. So you have to imagine something of the following sort. You have here your R equals 1, which is the boundary of W, that's R, right? This is the wall that you have picked, right? And your Floer trajectory is not contained inside here. So necessarily, because at plus and minus infinity, it goes to some asymptotes which are contained in there, right? R composed with U is going to have an absolute maximum, right? Then, since U of plus minus infinity is contained in K, the function R sur Q is going to have global maximum. Yeah. So let's compute. We're going to find the contradiction because I'm going to show that R sur Q is a plurisubharmonic, is a subharmonic function. Yeah. So we'll show that Laplace of R sur Q is positive. And this will lead to a contradiction, because if you have such a thing, that's going to hold on some domain that I'm not going to specify. If you have such a thing, maximum principle tells you that the maximum is attained of the boundary of the domain, right? But you can take the domain to be something like that, so that the maximum is going to be well above, right? So that's not, yeah. This will be a contradiction. Yeah. So now comes a very instructive computation. Namely, we decompose the Floer equation dsu plus j dtu and then minus xh. So xh is xar plus b, right? And this is minus the derivative times the rep vector field, right, with my conventions. in the region where we're interested, right? So that's minus A times the Reb vector field. So I'll right away replace it. Equals 0, yeah, on d by dr, r alpha, and psi. So let's see what we get. Yeah? So to decompose on d by dr, I have to apply dr to this whole business. Yeah? So I apply dr here, I get ds of r sur q. And then how does it go? Actually, this j, note that dr circ j, what does it do? So I take d by dr, and I plug it in and get a multiple of r alpha on which dr vanishes. So on d by dr, this thing vanishes. So now if I take r alpha, I get minus r d by dr, so that's minus r, and that's exactly the value of r alpha. So I'm claiming that this is minus r alpha, which I have also denoted by minus lambda. Do not forget that r alpha is the primitive of the symplectic form, right? So for simplicity, I will use this lambda as a... Okay, so dr circ j is minus lambda of dtu, yeah? And dr circ j is minus lambda, and when I apply it to this thing, I get a factor a and a value minus r, right? So I get minus a, and the value is r sur q, is my function. Agree? Because I'm looking at the point u. So that's on d by dr. Yeah? That's the component of the equation. Do you agree with this thing? Yeah? Okay. So now on r alpha, I have to apply to this thing alpha or lambda, right? So what do I get? I get lambda of dsu, yeah, and then lambda circ j is dr, yeah, plus dt of r circ q, and that's equal to 0. And then on psi, there's just pi psi dsu plus j pi psi dtu equal to 0. That's the system at hand. Yeah? So on psi, I just project this thing on psi, and then the projection onto psi commutes with j. So I just put it on the other side, and of course this guy will die when I project on psi. Yeah? So the two things that interest me are these guys, right? I'm interested in the Laplacian. So Laplace of r sur q, how will I do it here? Well, okay, never mind. R sur q, so that's going to be d2s r sur q plus d2t r sur q. Yeah, and so I have to differentiate with respect to s this first thing. So now I can write further. Oops. Right, I can write further ds for the first term of lambda dtu, and then I have this thing, so plus a dt of r circ u, right? No, ds, sorry, ds. Yeah, R sir Q. And then I have just another term, minus dt lambda dsu. Right? So what's this guy? So if I pair these two terms with each other, you see I have two vectors, ds on lambda dtu, dt lambda dsu. So what I'm actually computing is d lambda on dsu and dtu, and then I have to add lambda on the bracket of dsu with dtu, right? And then I have this guy, a ds r sir q, and it's good because ds and dt commute at the domain, right? We're in coordinate charts there. So this thing is going to be 0. It's going to go away. And this thing is going to be very nice because I know that dtu solves the Floer, u solves the Floer equation, so I can replace dtu by j dsu minus j multiplied by j goes away minus ar alpha, right? And that's good because R alpha is going to kill is going to kill okay, let's write. It's not really going to kill everything, right? So, so here I have d lambda of dsu j dsu, so that's norm dsu squared. That's very good. And then I have minus d lambda of this guy. So I have a, and then dr wedge alpha on dsu dsu r alpha, right? And then plus a ds of r sir q. But that's very good. So the only way I can get something which is non-trivial is by pairing this with this and this with that, right? So I get norm dsu squared and then minus a ds of r sir q and then plus a ds of r sir q, and these go away, and I get norm dsu squared, and that's positive. It looks like I've been making a slight error in my notes, but so I don't think I made any mistake, right? Yeah, I'm a bit puzzled by the fact that these guys kill each other, but we do not, right? Is there something? Derivative of h. Well, here h is just a fixed Hamiltonian. It does not depend on s or anything. Yes. Yeah? I think it's good. I think it's good. So, but one remark, we wouldn't have had to worry. So it may look to you like, oh, what a miracle. That's not the case. So even if these guys would not have canceled with each other, what we would have obtained would have been Laplacian plus some first order term bigger equals 0, right? So as long as you have an elliptic operator, right, without zero-order terms, it's fine. Yeah? Maximum principle holds. So the cancellation of these two guys has strictly no influence on the argument, right? It's just something that makes the thing look nice in the end. But it would have been as true that the maximum principle holds even if these two guys would not have cancelled with each other. Okay? Good. So, so this finishes the proof of this maximum principle. And now an adaptation, which I will leave as I think a useful exercise. And it goes again by decomposing the equation along d by dr, r alpha, and psi, is to show that proposition, yeah, assume you have not a fixed Hamiltonian, but a family of Hamiltonians which depends on S, right? Assume U defined on some omega with values in our R infinity cross blah satisfies dsu plus j dtu minus x h S, H of S and R, U equals 0, right? So before, there was no dependence on S, right? And this guy is contained in the cylinder. So there's a coordinate S and the coordinate T, right? So this is the S. So before, there was no dependence on S, and this H was just linear of positive slope, okay? So if d2h by ds dr is bigger or equal 0, then Laplace of r sur q plus first order terms plus I would say there exist functions a of st, b of st, such that Laplace plus a of st ds of r sur q plus b of st r sur q up dt r sur q is bigger or equal 0, and hence the maximum of u is attained on the boundary of omega. Yeah. So it's really the same computation, except that you now have to keep track also of this tiny dependence in S. Yeah? Where? Here? Oh, well, sure I have. I mean, it's yeah, all right. That's true. I agree. I agree with you. Yeah. I use the fact that it has this special behavior. It preserves psi. It's right. It sends RD by dr onto the red vector field.
The fact that dr composed j equals minus lambda is equivalent to the fact that j maps r dr to the red vector field.
And preserves psi.
No?
Okay. All right. Good.
Sorry, no.
I think you must preserve psi.
And preserves psi,
but not necessarily constant with respect to r on psi. Yeah. Okay. Mm-hmm. So, right. So reference for this, if you wish to have a proof, you go to Gilbert and Trudinger. and you find it. Not the computation, the fact that the maximum is attained on the boundary, right? So why am I thinking of such things? It's because something which has not appeared explicitly up to now in any of the lectures. It is the construction of continuation maps, right? So given two Hamiltonians, let's say HA and HA prime, both with non-degenerate orbits, non-degenerate one-periodic orbits, right? One can choose an increasing homotopy, and by homotopy I mean something like HS, such that for S close to minus infinity, HS is HA. For S close to plus infinity, HS is HA prime. And of course, such that outside a compact set, HS of R of T, R, and X is some little hs of R with d2h by ds dr positive. Of course, we can just choose some interpolation. For example, hs of R equals a of s, R plus b of s, right? With a of s increasing, right? So I just interpolate through linear Hamiltonians at infinity. And this condition is going to be satisfied, right? And then I can look, then we can consider for gamma minus a one periodic orbit of HA and gamma plus a one periodic orbit of HA prime, we can consider the moduli space maybe you have to also let J depend on S, but being independent on S at the endpoints, to be those U's which solve the Floer equation dsu plus J st u dtu minus x h st equals 0. And u of minus infinity is gamma minus, and u of plus infinity is gamma plus. Yeah? And this, so let me also write on the blackboard what I said orally with JST, such that JS T is independent of S and T outside and cylindrical, outside compact set, and independent of S for S close to infinity, respectively for S close to plus infinity. And given these moduli spaces, so note that the dimension of such a moduli space is going to be given by the difference of the indices. And so it's going to be the degree of gamma minus minus the degree of gamma plus. And there's no -1 as in Morse homology, because, of course, I cannot quotient by an action of R anymore, because I have this dependence on S. Right? And this defines so-called continuation morphism. Yeah, say phi from the Floer complex of HA with J, say JA, to the Floer complex of HA prime, JA prime, by sending gamma minus to the sum of gamma pluses, such that the difference of indices is 0, and you count the number of elements in this moduli space. Yeah. And thanks to the previous compactness argument, this condition ensures that this is well defined, right? For example, this thing is finite because in dimension 0 I have compactness up to broken trajectories, and hence a finite number of elements, right? So compactness is absolutely essential, and you see that we use crucially the fact that at infinity the homotopy is increasing, right? Through this condition. As a matter of fact, this is how you prove invariance of Floer homology, as defined by Mihai in his first lecture on the choice of Hamiltonian diffeomorphism, right? So he defined for any Hamiltonian diffeomorphism some Floer homology group. And then he claimed, well, this recovers the homology of the manifold, right? In particular, it's independent on the choice of H, right? And the reason why it is so is that if you choose two H's, you can interpolate between the two and build such a continuation morphism. In the compact case, such a continuation morphism is going to be an isomorphism, because you can run backwards, right? You're also allowed to interpolate the other way. And if you compose the two, you're going to be able in the end to prove that it's an isomorphism. Yeah? In this case, the continuation morphism is not an isomorphism. And you know it's not because for example, for the ball, you saw that once you cross this critical slope given by a multiple of pi, then you are grilled, right? The homology group is already jumps in some other degree, right? So the two will still be of rank 1, but they are not going to be isomorphic for degree reasons, right? So this is not an isomorphism. Similarly, if you believe the theorem that that symplectic homology of the cotangent bundle is the homology of the free loop space, right? The homology of the free loop space is supported in infinitely many degrees. It's infinite dimensional, right? And at every given slope, you get something which is finite dimensional. So of course, this must be not an isomorphism, right? It's going to grow. Yeah? So this is an important difference of this non-compact situation compared to the compact situation. Yeah? Continuation morphisms are not isomorphisms, and you know that. Yeah? And you can read that also in the other way, namely, if you try to do a homotopy which does not satisfy this property at infinity, you know that compactness will fail. Okay? You know that, because if it would not, it would be an isomorphism. Okay? So you have a footprint of loss of compactness, yeah? And it's a type of loss of compactness that's not been studied. All right. So, yeah. So I think now you have all the ingredients for the definition of this homology group. Yeah? I am trying to move ahead towards giving you an idea on how you prove this functoriality, right? Which was really at the core of the applications. So first, so now concerning properties of symplectic homology. Yeah. So the first property that I want to discuss is that you have a map from the relative homology to the boundary, or from the cohomology to symplectic homology. Yeah? Where does this map come from? Well, it comes from the following fact. Pick. So, again, picture. We have here r equals 1 and the boundary, right? Symplectic homology is a direct limit as the slope gets higher and higher, right? Yeah? This is how we defined it. But of course, there's all these continuation maps, and in particular, there's a continuation map from the Hamiltonian H epsilon. Epsilon being a tiny slope. Yeah? So pick epsilon such that epsilon is smaller than what I will denote T of the boundary, which is the minimal period of a closed characteristic. Of course, there is a minimal period for a closed orbit because the vector field that we're dealing with, the Reb vector field, has no zeros. So a closed orbit must have period bounded from below by something positive. So pick something tiny, slightly smaller, right? So of course then we have a maps from Floer homology of H epsilon into the Floer homology of HA for all A bigger than epsilon. And if you pass to the limit here, you get a map in the direct limit. You get a map from the Floer homology of this guy to symplectic homology. Right? But what's the Floer homology of this thing like? It's a C2 small function, right, which has a very tiny slope. So inside the W, since it's C2 small most function, the one periodic orbits are going to be just the constants. And outside, there's not going to be anything, right? So already you see that it's a good candidate for recovering the homology of the manifold because the generators of the complexes are critical points of a Morse function. Yeah? So the claim is that Floer homology of this H epsilon is the relative homology or the cohomology. Yeah. So why is that? Let's be a little bit more precise. So this H epsilon is C2 small Morse function on W and is equal to epsilon r, say, plus some constant, and we can assume that holds on the whole semi-infinite cylinder that we have added, right? Because I see too small, never mind, I can choose epsilon even smaller so that it really goes to the boundary with that slope, which is small, right? So what are we, so the fact is that in this situation, yeah, because there are no holomorphic spheres, so omega vanishes on pi 2 of the manifold, right? Then the Floer complex for H epsilon with respect to some j, which is independent of time, yeah, reduces to the Morse complex. The Morse complex. For this viewed as a Morse function. Yeah. Let's see what, so why is that? You see that if I pick, so if J is independent of time, right? If I write this thing, dtu minus xh epsilon of u equals 0, this I can still write as dsu plus j dtu minus the gradient of h epsilon. Right? Jx, with my conventions, is the gradient. Yeah? In Mihai's lecture, it was minus the gradient. So you see that if ever u does not depend on time, this guy goes away, and you end up with the equation of a gradient line for this Morse function. Right? So the game is to show that indeed all Floer solutions are independent on time. Right? And this for this I just give I give a wrong proof, but nevertheless which says something heuristically. The claim is that every Floer trajectory is independent on time. Yeah, and a heuristic proof, which is almost correct, is the following: if there exists a J independent on time, if there exists a J which is independent on time and regular, meaning that all moduli spaces are cut out transversely in the sense that Mihai has explained this morning, right? So the linearization of the Floer equation is a surjective operator for every solution, right? Then what do you have? Then you see that on any moduli space, so when I use this, I have already quotiented out the R action, right? There is an S1 action. Of course, if J is independent on time and H is independent on time, the whole equation is independent on time. And then you can shift around the trajectory and you're good. So whenever there is a point in the, whenever there is, so right, if ever there is a Floer trajectory which depends on time, its shifts are going to be solutions to the equation as well. So you get automatically a one-dimensional family. But you want to count in the differential just isolated trajectories. So these trajectories that depend on time, yeah, would not be seen by the differential. So the heuristic proof is for the fact that for every Floer trajectory of index 1 is independent on time, right? So this rules out time dependence on Floer trajectories of index 1, yeah, which are isolated. Yeah? But of course, this is not a true proof. Yeah, the proof goes a little. So if you wish to see how the proof goes, you should go and look at Salomon Zender. Sorry? Yeah. You have to prove existence of this thing, but actually in the proof of existence of that thing, you implicitly also prove that these guys are independent on time. So, yeah. So now that we know that all Floer trajectories are independent on time, what do we see here? This term goes away, and we are left with this u of st is, how should I call it? Gamma is not good, it's taken. V of s, yeah, such that dsv, or rather dv by ds, that's even better, equals positive gradient of v. So you see, secretly, I'm computing, I'm using a positive gradient, right, with my conventions. So this gradient vector field points outwards along the boundary, right? And I'm using a positive gradient, so this thing recovers, because it points outwards along the boundary, the cohomology of the manifold. Yeah? So since points outwards along boundary, the equation dv by ds equals grad h epsilon v computes the cohomology of the manifold. And the degrees, so now I can correct this. It's not actually this, it's cohomology, and as a matter of fact, because of the conventions, it's in that degree. So that's the map. Yeah? That's the map. That's the map. Questions? Sorry? Yes. So this is something puzzling in the literature. So my SH, I mean my, it's not mine. So this version of SH star is what Seidel denotes SH n minus star. Yeah? So I call it, so, and now this is somehow a matter of taste. This is a good notation for algebraic purposes, because you want something that's a ring to be a cohomology object. and the map C star becomes a degree 0 map, right? From the cohomology in this degree to the symplectic cohomology in this degree. Nevertheless, with this convention, you emphasize the geometric content of the object, because this is such that you have an isomorphism with the homology of the free loop space in that degree. So one can argue in favor of one or the other. But indeed, it is a matter of convention how you call it. But what you compute for an epsilon slope Hamiltonian is not a matter of convention. It's a matter of, it's what equation you use. It comes out, okay, from your convention of signs, but I mean, calling this homology of cohomology is a matter of convention. But what you compute for epsilon slope, you have no choice. You have to call it what comes out of your sign conventions. Yeah, if you choose to work with the relative thing. Indeed. So now to functoriality. Yeah, I really can't do it faster. I think it's okay to do it this way. I mean, it's, yeah, I'm behind what I wanted to tell today, but never mind. Okay, so about functoriality. Yeah, about functoriality. So what do we have here? The setup is that of an inclusion. Yeah? And the key picture that we want to consider is the following. I have V, that's the boundary of V. Somewhere outside, I have the boundary of W. Yeah? And inside V, I have some coordinate given by the Liouville vector field, right? And outside W, I have completed, right? And I want to consider Hamiltonians which have this form. Whoop, whoop. And this I have to say something. It can't go whoop up to all the way down because I'm not on the ball in Cn, right? So somewhere I hit the place where bad things happen. So the only way to solve that is to say that it becomes constant eventually. Yeah? So up to where am I going to go? Up to some parameter delta that's going to have its importance. Yeah? And I'm going to call these slopes mu and nu, if you do not mind. Yeah? So what I've drawn here, you all agree, is a Hamiltonian. Yeah? It's a function defined on this, on W hat, right? So this whole thing is W hat. Okay? And what I see here is, if you wish, that's 0, 1 cross the boundary of V, right? Inside the smaller Liouville domain lives, right? Lives the small part of the symplectization, the one that has finite finite volume. So that's V, and this whole thing is W. Okay? That's the picture, and I want to consider this Hamiltonian. So let's think for a second, what type of periodic orbits do we see on this Hamiltonian? All right? So here, it's constant. We're going to see, when I draw a constant, you have to imagine that I perturb it a little bit. so that it becomes a C2 small function if you want to achieve non-degeneracy. Yeah, but let's not worry about that. So this is a first type of periodic orbits, constants. Then in this region, yeah, it depends on the radial coordinate as I drew it, right? The Hamiltonian vector field is proportional by the slope to the Reb vector field on the boundary of V. So I'm going to see maybe some periodic orbits there, right? In here, there's no periodic orbits because this is going to be chosen and not to be equal to the period of a closed characteristic. But out of a sudden, the slope starts to vary there, yeah? So maybe I'm going to see some periodic orbits. Let's label this group by 3. Yeah? 2 and 3. So now, here it is constant. So I'm going to see constants. It's going to be C2 small. Yeah? And here the slope starts to vary again. And we're going to see something else. And these are going to correspond to periodic closed characteristics on the boundary of W. Yeah? So you may wonder where I want to go with this guy. Imagine that this thing does not exist. What you see here, up to this rescaling, is the type of Hamiltonian that computes the symplectic homology of V, right? So now we are allowed to modify a Hamiltonian without changing the result of this Floer homology group. So this can be seen as a compact perturbation of your Hamiltonian. So if you imagine that so what this whole thing is going to compute is actually the homology of this thing, right? So secretly in this picture, you see also hidden the symplectic homology of W, right? There's this, there's that. How to separate them? Of course, there's a big thing, and we want to separate them by emphasizing some subcomplex. And the natural way to do that is using the action, right? Because the action decreases along Floer trajectories. So the sublevels of the action form subcomplexes in a natural way. Okay? So let's compute. It is instructive. So let's now maybe, yeah, right. What are we going to go? So for one, let's not forget my convention for the action is minus the integral of x star lambda minus the integral of h of t x of t dt. Okay? So also recall that the Hamiltonian vector field of something that depends only on R is minus h prime times the Reb vector field. Right? So hence, if x is periodic, one periodic orbit of xh of R on level R, you get that the action of x is what? Well, you have, here you have to integrate, so you evaluate lambda on this guy, right? So you see popping out an h prime, and then lambda on R alpha is little r. And minus with minus is plus, so you get h prime of R times R, and then minus h of R. Right? That's the formula. That's for computing. Yeah? And the fact that this form, not that this formula, that the primitive of the symplectic form is defined globally allows us to compute actions using the same formula both here and here. Yeah? I insist on that. So what about the first one? Here it does not, there's no slope, so the first part goes away. And the value is, I have gone from 1 to delta. So it's the value is minus mu times 1 minus delta. Right? That's the value of the Hamiltonian there. And therefore, the action is mu 1 minus delta. Right? So for 2, I have this as a reference point. So mu 1 minus delta. And then what I have to add, so I can see periodic orbits between the smallest period and the highest period at most equal to mu, right? So plus the delta times the smallest period of a closed characteristic on V, and then mu 1 minus delta plus delta a priori mu. Yeah? Yeah. As a matter of fact, note that since mu is different from the period of a closed characteristic, then it means that there exists then the distance from mu to the set of periods, which I call the spectrum, yeah, for the boundary of V, is positive. I denoted eta mu, and that's positive. Yeah? So actually, the biggest thing that I can see here is not really mu, but it's going to be eta mu. Yeah? And it's going to play a role in a second. Yeah, this tiny, tiny gap. Yeah? So what about 3? Well, in 3, the value of the Hamiltonian is very close to 0, so I'll just ignore it, right? And the slope varies from mu to 0. So I have an action which is contained in this interval. Yeah? So what I'm computing here are actions. Yeah? So 4, that's easy. That's 0, essentially, right? I have constants, and the Hamiltonian is equal to 0 there. And 5, well, again, I compute. So here R was equal to 1, and here R becomes 1 again, right? So it's a different R. And therefore, it's contained in here. Period of the smallest characteristic, and then nu. A priori is nu minus eta nu, but I don't need that. Yeah. So after this glorious computation, I'm going to be able to order things according to the action. So everything is positive here, right? The smallest action is 4. So next, what do I see? Well, a priori, I do not, mu is large, right? So these guys are large. The first things that I see are 3 and 5, and there's no way I can separate them by the action, because I have no control on where the first closed characteristic appears, neither on the boundary of W nor on the boundary of V. So 3 and 5 I have to treat for the time being together. Nevertheless, so 1 is smaller than 2, obviously. And this I can achieve, right, provided, so for 5, I need that nu be smaller than than this guy, right? Mu 1 minus delta. Say nu smaller than mu 1 minus delta. Yeah? And also, most importantly, I need this guy to be smaller than that. So mu minus eta mu smaller than mu minus delta mu, i.e. delta, this goes away, delta has to be smaller than eta mu over mu. Yeah? So I have some freedom on these parameters. Yeah? And I have not said up to where I want to go down with this Hamiltonian. Now we have the answer. Once mu is fixed and nu is taken a little bit smaller than mu, yeah, I must go down deeply, right, so that this relation holds. Yeah? Yeah? And you see that here it was important to take into account this tiny gap. Yeah? So that's good. That's very good. Because now we can write some complexes. So let me write the following. I want to write several things. So I want to write first the total one, and then what comes to the left, 4, 3, and 5, is a subcomplex. 4, 3, and 5. Yeah? And I take it to be truncated smaller than nu. I have the right to do that. Right? So what's in the left is a sublevel. If I truncate at nu, somewhere here, it's a sublevel of the action, and therefore is going to form a subcomplex. So what I'm left with is this guy. 1, 2, and 3, part of 3 which is bigger than nu. And that's an exact sequence, of course. Subcomplex, quotient complex. Now, inside here, 4 is the smallest, so I'm going to write it 2. 4 is the smallest. It's a subcomplex, right? And what I'm left with is 3 and then 5 truncated to smaller than nu. Now is going to come something trickier. I want to write 1, 2, 3, and 4. So that's bad. Yeah? I'm contradicting myself almost, because I have no way of separating by the action 5 from the other guys. Nevertheless, I'm claiming that 1, 2, 3, and 4 form a subcomplex. Yeah? I'm claiming that. Wow. So what I'm left with here is 5. And there's like this. Yeah. And then I want to write one. What do I want to write? Yeah, 1, 2, and 3, the full of it. Like this. There's just a map. And these guys form an exact sequence. I'm sorry. I've heard that one. And I just here it's not really, there's no map here, right? There's no maps. That's what we have at our disposal. Yes? I'm using something, right, so let me maybe claim. Yeah, I'm using a form of maximum principle. Yeah? C1, 2, 3, and 4 form a subcomplex. Yeah. Yeah, let me finish, let me leave this for later, yeah? But I'm claiming that, indeed. But there's something that I would need to prove. Maybe, yeah, I'm going to give a heuristic explanation, and heuristic. No, it's not a heuristic explanation. It's a lemma, which I will probably not prove. Lemma. So assume U is Floer trajectory asymptotic at plus infinity to something in 5, yeah, and at minus infinity to something, no, let's not say anything here, something in 5. Then unless U is constant, yeah, there exists some S and T in R cross S1 such that R circ U at ST is bigger than R of the asymptote. Yeah. So what I'm saying here, in other words, U approaches an asymptote at plus infinity from above. Yeah? That's the statement. And I think I will not, so for a reference, we have a paper with Frédéric Bourgeois. It's called Long Exact Sequence Relating Symplectic and Contact Homology, and it's in there in section 5. Yeah? And it's a form of maximum principle. Yeah, actually, yeah, no. To prove this result is not a form of maximum principle, it's a computation that comes out of the special form of the Hamiltonian and the fact that H is convex. That's what we use here. Yeah, H is convex.
So it's not action filtration?
No, no action filtration. It's something specifically related to this type of Hamiltonian depending only on R, to almost complex structures that are cylindrical, and to the fact that H is convex. That's what we use. Yeah? And it comes from decomposing the equation and arguing by contradiction. We use Stokes' formula, decompose the equation at some point, and yeah, you argue by contradiction. So nevertheless, once you know that, you're done with the fact that these guys form a subcomplex. Because if there would be a trajectory coming from one of these guys and asymptotic to 5, it would have to come from above. But that is forbidden by the maximum principle, because it would have a maximum over here. Right? So this lemma plus the maximum principle ensures that this guy forms a subcomplex. Okay?
So what it means to get this subcomplex, you don't, it's not only action filtration, you need these
Yes.
X ingredients.
Yes. Yes. In order to get this subcomplex, all the other guys are fine. Yeah? But for this one, I need this additional geometric ingredient. Yeah? Okay. May I take 5 minutes? So, I want, let's think a little bit. So now it's going to be a little bit of heuristics. What does the complex 1, 2, 3, and 4 compute? Well, I have this guy, 1, 2, 3, and 4. I can deform the Hamiltonian inside. It's possible. So if you imagine, it's just computing the homology of a Hamiltonian, which is essentially 0, a C2 small function in here, and then starts to grow. So that's the cohomology of W. That's cohomology for W, yeah, by this deformation argument. What about 1, 2, and 3? 1, 2, and 3. So you see, the orbits that appear in 2 are geometrically really the same as the ones that appear in 3. They correspond to the same characteristics. As a matter of fact, these come so well together that if you deform the Hamiltonian, they will just kill each other. Yeah? So as a matter of fact, 1, 2, and 3, these guys actually kill each other, and it's like computing the homology of a C2 small function on V. Cohomology of V. Now, what about 4? Yeah. Well, 4 is on the nose the homology of a Morse function such that the gradient exits to the right and enters to the left. So that's going to compute the relative cohomology of this part relative to this thing. So this is cohomology of W relative to V. Well, it's of W minus the interior of V relative to the boundary, but I can just write it as such. Okay? That's good. What we have obtained up there is the long exact sequence in cohomology. Yep. So let's see now, for the total complex, I have already told you that, okay, up to deforming this guy, we're actually computing the homology of a Hamiltonian, right, which is one of those that gives you a symplectic homology of W. Of course, you have to pass to the limit accordingly, but up to passing to the limit, this is going to give you homology of W. And 1, 2, and 3, 1, 2, and 3, well, I'm looking at, so the part in 3 that's bigger than nu is going to kill the part in 2 that's bigger than nu. So it's like computing 1 and 2 in action smaller than nu. But we will also let nu go to infinity. So that part is going to compute symplectic homology of V. Yeah? What about 4, 3, and 5? 4, 3, and 5, well, that's a definition. I'm going to label that, and I'm going to write the formal definition just right there. I'm going to label it as such. There's something. Yeah? Have the right to give it the name, and it's going to complete that thing. Right? So what about these guys? Well, 5, yeah, is like the part of symplectic homology that's generated just by the dynamics on the boundary. So it rightfully deserves the name which I have not introduced up to now, SH plus of W. Yes? Yeah? All the rest go away, and I'm just talking about 5. Yeah? It's just the dynamics on the boundary of W. What about 3? The part of 3 that's smaller than nu. It's the dynamics on the boundary of V up to action nu. It rightfully deserves the same name, right? SH plus of V. And this is going to deserve the name SH plus of W rel V. Yeah? Yeah. So what do we see here? We see 2 short exact sequences of complexes and then a commutative diagram of short exact sequences that's going to induce a commutative diagram of long exact sequences in cohomology. Right? So from this thing, you get cohomology of W passed to the limit. Yeah? And then cohomology of this, cohomology of V, and then come these other guys. These are related by maps, and this is going to commute. Everything is going to be working fine. And as a matter of fact, you already see here exact sequences, right? So you will be able to complete at least these columns to long exact sequences. And this one just stands on at the wrong place. Yeah? If it would have been the other way around, so this guy first would inject in here and would project in there, it would be an exact sequence. But that's just an instance of what's called in homological algebra rotating triangles, rotating distinguished triangles. Yeah? So in the end, you're going to get a big grid diagram, which I adore. Yeah? Plus W, SH plus V, and everything is going to be connected. So here we use a bit of homological algebra and the cone construction. Yeah? And everything is going to be connected, and the lines and the columns are going to be long exact sequences in cohomology. Yeah? So this part, which is absolutely fully proved now, gives you, in particular, this commutative square, and that's the one that I have used, yeah, in the proofs. This is Viterbo's commutative square in his GAFA 99 paper. Yeah? But this commutative square can be completed, right, by viewing these maps, inserting them into exact sequences of a pair. Right? And these guys inserting them in what I call tautological sequences. Yeah? So I will have to decide, but on what direction to go tomorrow. But these guys, the plus things, are directly related to what is called contact homology or linearized contact homology. Yeah. And you see, actually, the structure that appears at this point is the following. Whenever you have an inclusion of Liouville domains, you have an exact sequence of a pair, and this can be generalized even to cobordisms. Right, and in this vein, you can make sense of analogs of the Eilenberg-Steenrod axioms, which are subsequently useful for computation. Yeah, so I think I will just stop.